Okay, we've got a transformation from a vector space V to vector space W. Okay, it's T from V to W, where V has basis B, W has basis B prime. We don't assume that the vector spaces have the same dimension. Dimension n here, dimension m here. Well, the vector V can be represented relative to the basis B. Whatever the vector V is, it's some linear combination C1, V1 through Cn, Vn of the vectors in the basis B. Okay? And the transformed vector is some linear combination of the vectors in W. And given the transformation, we want to know what the matrix is that we would use to multiply the vector C1, Cn with respect to B, representing the vector C1, V1 through Cn, Vn. Okay? In terms of the basis W1 through Wm of the W space. So that means we'd want to write T of V, T of this V with respect to this basis, and get the components of the vector with respect to the other basis, meaning we would get a D1 through Dn, let's say, such that the transformed vector is D1, W1, et cetera, up to Dm, Wm. Well, I started writing this down, knew what I wanted to say, and got confused about just how I wanted these components to appear in the matrix. So, yeah, I was legitimately confused. I figured, well, I can do this. Well, I do that a lot. So I did just exactly what anybody would do if they had any sense trying to solve a problem like this. Bring it back to a simpler problem. This is a generalization of what happens that can be more easily understood in terms of a transformation from R2 to R2. So let's just take a specific basis for R2 and another specific basis for R2. And we've got a transformation from this R2 to this R2. And the transformation is defined by T of xy equals x plus y minus 2x. Okay? Well, if V equals xy, just to give us a context, we're not actually going to use this, but let's just see for sure we understand what this means. If V equals xy, then V with respect to B, which we write as C1, C2 with respect to B, is the vector with the property that this xy, the actual components of the vector V, is a linear combination of vectors from the basis. A C1 times the first vector times our V1 vector, I'll call this the V1 vector, and C2 times this vector, which I call the V2 vector. Okay, well, now we want to know that if V expressed with respect to B is C1, C2, that means, of course, that V equals C1 times V1 plus C2 times V2. Maybe I'll write that out, C1, V1 plus C2, V2, just so we have reference for all the notation when we attempt to write this one down. Okay? So there's our vector V. Now, T of V is what? Well, T of V is going to be C1 times T of V1 plus C2 times T of V2. Okay, well, the question is, what's T of V1? What's T of V2? Well, T of V1, very straightforward, is 0, negative 1, using this rule with the vector V1 is 1, negative 1. So using this rule with this vector, here's what we get. T of V2 is this. And again, we just use this rule with this vector, and we get this. Okay? Then T of V is C1 T of V1 plus C2 T of V2. Well, I didn't write it down. Because we can easily calculate it. But what linear combination of vectors in B prime gives us T of V1. What linear combination gives us T of V2? Well, I wrote it down, but I didn't write out the calculations. I just did this by inspection. I just looked at these two vectors. Okay, T of V1 is T of 1, negative 1. Okay, T of 1, negative 1 is 0, negative 1. That's our T of V1. So there's our T of V1. That's what linear combination of the vectors in B prime? Well, to get 0, negative 1 from these two vectors, I just look, well, if I add these two vectors, I get 2, 0. I get 0, 2. Okay? I want to get 0, negative 1. So I take negative 1/2 of the sum of these vectors, and I conclude that T of V1 is negative 1/2 W1, that negative sign maybe needs to be a little more prominent, minus 1/2 W2. So that would be negative 1/2, negative 1/2 is expressed with respect to basis B prime. Now V2, well, playing around with these vectors a little, I see that if I subtract these vectors, I'll get a 0 here. And T of V2 has a 0 here. So I know I'm going to want to subtract some multiple of these vectors. If I subtract them, I get 2, 0. To get 3, 0, I take 3/2 of that, and I get my T of V2. So that's 3/2 W1 minus 3/2 W2. And of course, that can be written as 3/2, negative 3/2 with respect to B prime. Now we come over here, it then follows that T of V is expressed with respect to B, and remember B with respect to B is some C1 V1 plus C2 V2, so that it's T of C1 V1 plus T of C2 V2, which is C1 T of V1 plus C2 V of T2, just linearity property. But T of V1 is negative 1/2 W1 minus 1/2 W2, and T of V2 is 3/2 W1 minus 3/2 W2. So I've got C1 times negative 1/2 W1 minus 1/2 W2, and C2 times T of V2 is C2 times 3/2 W1 minus 3/2 W2, which then combines to give me negative 1/2 C1 plus 3/2 C2 W1 and so forth, just putting these together and collecting the W1 and W2 coefficients. Okay, so the matrix I want to take the B representation to the B prime representation is going to be the matrix that are multiplied by C1, C2, my B represented with respect to B, and gives me the negative, well, this vector, okay? Because, of course, this vector expressed in column form is this multiple of W1, well, that goes in the first row, and this multiple of W2, and that goes in the second row. Okay, so the matrix I need to multiply C1, C2 by to get this, in other words, then I multiply the representation with respect to basis B by to get the representation with respect to basis B prime is, well, it's obvious what matrix I need to put there. You can look at this and see what the matrix ought to be just as easily as anybody, okay? And you see that if I multiply this column by negative 1/2, 3, 2, I get this. Multiply by negative 1/2, negative 3, 2, I get this. Very easy to see. Well then, we're going to say that if T of V1 equals A11 W1 plus A21 W2, and T of V2 equals A12 W1 plus A22 W2, then the vector expressed with respect to B prime, this thing, is equal to the matrix that's formed by the AIJs multiplied by the representation with respect to B. Well then, I generalize this to the situation I have here. What do we have? Okay, same situation, and we assume we know what T of V1 and T of V2 and so forth is. So we say that if T of V sub I equals AI1W1 plus and so forth up to AIMWM, then V with respect to B prime is the Aij matrix multiplied by the vector with respect to B. And this is how we go directly from representation with respect to B to representation with respect to B prime. And this is the representation of the matrix, of the transformation, whatever the transformation is. Okay? And of course, I guess I could write this a little more in detail, just to remind us that the Aij consists of the T1, not T1, T of V1 vector. That'll be your first column by this and the subscripts, and you can see how that works. And then the second column will be T of V2, and the last column will be T of V N. Just making sure my dimensions are right. Okay? This is an n-dimensional vector, or an n-dimensional, an n by m matrix. Okay? Because every one of these T of V's gives you an m-dimensional representation in terms of W1 through Wm. Okay? A linear combination of the m vectors in the basis of your W space, the B prime basis. So that's pretty much it. If you're given a transformation, you do kind of what we say here. There's your transformation. You can kind of skip all this stuff if you just want to follow a rule, but if you want to understand it, you kind of think it all the way through, at least until you're sure you're always able to think it all the way through. But this tells you you're just going to calculate T of V1 through T of Vn with respect to the B prime basis. So really, I should have put a B prime on each of these. To be clear. As we did here, we calculated T of V1 and T of V2. Then, using techniques that we know quite well by now, we express each of these vectors in terms of this basis. That'll be our T of V1 with respect to B prime, T of V2, and so forth with respect to B prime. We do that. I did it by inspection. You might have to set up a matrix calculation if the numbers aren't as simple as they were in this case. But we get this. And then these become the columns of this matrix. And this matrix represents the transformation of coordinates with respect to B, giving us the transformed vector with coordinates with respect to B prime. So this is the matrix of T with respect to the matrix B, or the basis B, and B prime, and that's, of course, what this is.